Welcome, everybody. Thanks for coming today. Today is Dafang Wang's, did I get that right?
Correct.
Thank you. Ph.D. defense. Dafang has been here in SCIInstitute for 6 years, and he has studied with both myself and Mike Kirby. It's really been a team effort. The three of us meet every Thursday in the morning. And then also, he's been meeting with Rob McLeod's group on a regular basis, and also with Dana Brooks, who's the external examiner at Northeastern University, and Ross Whitaker is the 5th member of the PhD committee. So I was going to give you a bit of background about Dafang, but he has prepared a slide to do that for me. So I will turn it over to Dafang.
Okay, thank Chris for his nice introduction. Perhaps I will just restart this so can I get a good count of the time. So my PhD thesis is about the inverse problems in electrocardiography. So before that, a little bit about myself. I grew up in Hangzhou, which is a city at the southeast coast of China. And I got my bachelor's degree from Zhejiang University in 2005. And I came to SCIInstitute in 2006 and became civilized. And now then I start working in front of computers every day. So my work is on the electrocardiography, or ECG. So the goal of ECG is to diagnose activities of the heart. The current practice is to place only a few leads on the chest of the body, and the trained doctor will try to interpret the recorded body surface signals. So because of its low spatial resolution, this current practice of ECG offers very limited information about what is going on in the heart. But often, the doctors would not only like to know whether your heart is healthy or not, they would also like to know whether any local regions of the heart is abnormal and to what extent those abnormality is. And that motivates the goal of the inverse problem in ECG, which uses computational models to compute the images of the electrical fields of the heart, of the whole heart. As shown in this figure, if we compare these two patients, if we only judging from their body surface recordings, then their signals are almost identical to each other. But if we can look at their electrical potential fields in the heart, then we can definitely see there are some abnormal things going on here. So such localized diagnoses are very helpful for nowadays medical treatments, such as those catheter-based interventions and stimulations. And therefore, the inverse ECG has a very promising clinical application. And for those of you who are not familiar with finite element methods, it is a numerical method for solving partial differential equations over irregular complex geometries. The basic idea is to decompose your domain into a group of regular geometries, such as triangles and tetrahedrons. And each of these geometry is called an element. That's the basic terminology for finite elements. And the overarching goal of my thesis is about finite element solutions to the inverse problem, and we pursued two goals. The first goal focuses on the formulation of the finite elements, and for which we carried out a case study for estimating the heart surface potentials. And the second goal is a new technique to be developed for inverse calculation called PDE constraint optimization. And we apply this technique to the case study of localizing heart disease called myocardial ischemia. And now I will talk about the first goal, and this is the outline. And the main part of work would be the finite element refinements for the inverse problem. And this part of work corresponds to my first thesis goal in my PhD thesis. That information is mostly for my committees. And to fulfill that purpose, we developed two techniques. One is called hybrid finite elements, and the other one is called high-order finite elements. And that part of work constitutes the second thesis goal in my thesis. So now a little bit background about cardiac electrophysiology. So the heart behaves as an electrical source in our body and has very regular electrical activities in each heartbeat. And these activities stems from the electrophysiological activities of the cells, which are characterized by the time sequence of its membrane potentials. also called action potentials. And this figure shows the action potentials of the cells at different places of the heart. And so these actions are all synchronized, and the aggregate effects of these cellular activities is an ever-changing electrical field in the heart, which creates electrical currents, which then propagates through the body volume and reach our body surface, where the signal is being recorded. So this mechanism forms the bioelectrical foundation for ECG diagnosis. And currently, there are three main heart source models being used. The classical approach is to use the potentials on the epicardial surface. And the advantage of this approach is that it enables direct experimental validation. But the inverse problem is very ill-posed. The second approach, also very popular, is to model the source as the activation wavefront during the heart. And in this approach, the unknown parameters that we pursue are the activation times at each point of the myocardium volume. This approach is less ill-posed than the first one, but its application is mostly limited to the activation phase of the heart. And the third approach, they consider the volume distribution of potentials within the myocardium. And this approach has a very great clinical interest because it characterizes the properties of the whole heart tissue. But so far, it has seen very limited progress because this is the most difficult approach among all three. And in this study, we look at the first heart model in our Go 1 and the third model in our second Go. So this is the mathematical model for the epicardial potential-based ECG simulations. And it has been described by a Laplace equation defined over the volume bounded by the heart surface and the torso surface. And the sigma represents the tissue conductivities, and the U represents the potential field. And in the simulation, once we're given these anatomical geometries, and the heart surface potentials comes in as a dirichlet boundary conditions, from which we can solve the partial differential equation, get the torso surface potentials, and then we can inversely compute the heart surface potentials and verify our results with our measured data. So this is the basic pipeline for the forward and inverse simulation. With finite elements, we can derive from the PDEs a so-called transfer matrix K, because this is the linear inverse problem. This transfer matrix K relates our heart surface potentials UH with our torso surface potentials UT. And the inverse problem is mostly about somehow inverting this transfer matrix. And the main challenge here is that the transfer matrix is notorious for its ill conditioning. Now I review some of the related works on the ECG simulation based on the epicardial potential sources. So overall, the development of this area follows two paths. One is simulation, and the other is regularization. On the simulation side, most of the early studies were using the boundary element methods. And starting from 1990s, people were gradually adopting the finite element models to account for the complex anatomical structures and the tissue anisotropes in the tissue. So, and on the regularization side, the work in the 1980s revolved around developing those basic regularization techniques for solving the ill-posed inverse problem, such as the Tikhonov regularization and total variation. And since 1990s, the research on this front mostly focused on some more advanced and fancy regularization techniques, such as the joint spatial temporal regularization or the imposition of multiple constraints. So overall, the trend in ECG simulation nowadays is shifting towards using complex, realistic, and anatomical models. And the finite element methods, I think, will becoming the predominant approach. And there's natural conflict between the growing model complexity and the ill-posed nature of the inverse problem. So there's a need to find a way to optimize the finite element formulation or the meshing, particularly for the inverse problem. But this question has yet to be addressed. And nowadays, most of the simulation people, they simply get some mesh that looks good from meshing people, and then start working hard on their simulation to try to tackle the ill conditioning and get some good results. But what we found is that actually the quality of the meshes or the quality of the problem formulation actually matters and in fact affects the accuracy of the solutions that you get. So that is the main motivation of this study. So we now look at the finite element refinement strategies that particularly for the inverse problem. So before that, I present a metric that we use to evaluate the ill conditioning of the inverse problem. In this term, it's with respect to the transfer matrix K, which relates your heart potentials to your torso potentials. So this is a typical curve of singular values of the transfer matrix K. And because it is ill-posed, there is a portion of its singular values which are very small, technically they are 0, and forming the null space of the transfer matrix. So this means any component of your heart potentials that falls into this null space are effectively smoothed out when they propagate to the body surface, and therefore are very hardly to get recovered. In that regard, a worse conditioned problem will be characterized by a curve shifting towards the left, where you have a fast decay of singular values, and you have a larger proportion of 0 singular values. And a better posed inverse problem will largely be characterized by a gradual slowing decay of the singular values. And hopefully we can get rid of most of 0 singular values here to try to lift them as much as we can. So with this metric in mind, we now look at the impact of refinement. And the motivation of this study is that an arbitrary refinement may actually become inappropriate for your inverse problem, such as the uniform refinement, which is being widely used in the forward simulation. Because in the forward calculations, as long as your computational resources permits, you can always create a very high resolution model to improve your approximation accuracy. But the consequence of such practice in the inverse problem is that you simply, first of all, you enlarge the size of the transfer matrix and extend its singular value spectrums. But most of such extension results in very small singular values and making this inverse problem more ill-conditioned. And on the other side, a sensible refinement may actually improve the conditioning of an inverse problem, such as in this case, we fixed the resolutions on heart boundary and on the torso boundary of all these 3 meshes, and we refined the volumes in between. And the consequence of such refinement is that it improves the singular value spectrums of the transfer matrix by largely shifting these small singular values up, and therefore improve the conditioning of the inverse problem. And such improvement then leads to more accurate inverse solutions. And in this diagram, we show the relative error of our computed hard boundary potentials compared to the ground truth. And as can be seen, the result from mesh C is about half the error as shown in mesh A. And in this figure, we plot the potentials on the hard boundary as a one-dimensional curve. And again, that shows that the inverse solution that you get from mesh C are closer and better than the ground truth than from the solutions from the cross mesh. So the question now is, what are the good strategies for the refinement for the inverse problem? Well, to answer that question, we conducted the Fourier analysis. And I will not go through the details here. And the basic message is that we used Fourier analysis to quantify the relation between the numerical ill conditioning of the problem and the discretization that we pursue. And what we found is that the degree of conditioning is an exponential function with respect to the highest spatial frequency of the hard potentials that we pursue. And that spatial frequency is dictated by the discretization resolutions. So therefore, given the resolution, we can estimate what's the conditioning of the transfer matrix that we obtained, and vice versa. Given an acceptable rate conditioning that we want to solve, we can estimate what's the maximum amount of resolution that we can pursue in our meshing. So based on this Fourier analysis, we developed basically 3 strategies for carrying out refinements for the inverse problem. Essentially, that says you should somehow constrain your resolutions on the hard surface in order to limit the conditioning of your inverse problem. And meanwhile, you need to sufficiently refine the total volume, but any over-refinement is not necessary. And the third point is that you should refine the high gradient field very close to the heart region. And this work has resulted in 2 publications, one in 2D study and one in 3-dimension study. And to realize these three refinement strategies, we developed 2 techniques. One is the hybrid finite elements, and the other one is high-order finite elements. So we now look at the hybrid. The problem here is we want to fix the triangulations on the hard surface, and meanwhile, we want to refine the region right next to the heart. And when tetrahedrons or triangular elements are being used, such a requirement usually leads to a very flat called sliver elements. And you can think of these base triangles represent the hard surface, and this extra node corresponds to the vertex in the volume. And from a numerical computation point of view, such sliver elements can cause numerical problems because they have very bad aspect ratios. And to tackle that problem, our solution is to put layers of quadrilateral elements in 2D or layers of prism elements in 3D, and so that we can decouple the refinement in the normal direction of those prisms and in the base, such as shown in this diagram. Let's think this is the hard surface, and we put 2 layers of prisms here. And the refinement in the normal direction can be achieved by using more layers of thinner prisms. And meanwhile, the triangular surface is being preserved. So in this simulation test, we refine the regions of 1 centimeter surrounding the hard surface by using 1, 2, and 4 layers of prisms. And we also compared our refinement with a case of a pure tetrahedral elements where no prism was being used. And the first finding is that the refinement in the normal directions around the heart effectively improves the singular values of this projection matrix that projects your hard surface potentials into the volume. And as can be seen, it effectively removes almost all the small singular values here and makes this matrix from ill-conditioned to well-conditioned. And in this diagram, we show the inverse solutions of epicardial potentials we get. And what we found is such refinement actually leads to a better recovery of the gradient field of the epicardial potentials. And in this case, we use a metric called R-grade, which measures the ratio of the norm of the gradient field of the our reconstructed epicardial potentials to the ground truth. And as can be seen here, such refinement improves this ratio from 76% to 91%, which means we can get largely 91% of the exact gradient field. So the second method that we looked at is the high-order finite element. The basic notion of a high-order element is to use high-order interpolation basis polynomials within each element. So the top figure gives an example of 1D modal basis and high-order finite elements. And the bottom figure shows the construction of high-order finite elements in the 2-dimensional quadrilateral elements. You can think of these basis functions are constructed as a product of 2 one-dimensional basis polynomials along each dimension. So any small figures here corresponds to 1 basis function. So here we have a 5 by 5 basis functions. And these basis functions can be largely decomposed into 3 modes: the vertex mode, the edge mode, and the face mode. And for the vertex mode, each vertex mode is non-zero only at 1 vertex where it is being located, and then linearly decays to 0 to the rest of the element nodes. And for each edge mode, it is non-zero only at one edge of the element and not zero at the rest edges. And for the phase mode, it is only non-zero within the element and not zero at the boundaries of the element. So these different kinds of modes can be schematically represented by a diagram shown here, that each red dots represent the vertex mode, the green dots for the edge mode, for the phase mode, and blue dots for the edge mode. And in comparison, a linear finite element would be characterized by only 4 vertex modes. And in a similar manner, we can define the high-order basis functions for triangular elements and show their diagrams in this way. So with this representation of high-order modes in place, we now look at how we carry out our high-order refinement for the inverse problem. Just think of this domain that we consider, and this edge represents the torsal surface, and this edge represents the hard surface. We now have first-order linear finite elements. And let's say now we do a third-order finite element refinement, and that is the spatial distribution of all our high-order modes. But remember, for our inverse problem purposes, we want to maintain a low-order approximations on hard surface and torsal surface in order to constrain the conditioning of our transform matrix. And how can we do that? The way that we maintain this, we call selective refinement, is that we simply remove all these extra edge modes on the hard surface, or effectively at any place where we want to maintain a low-order approximation. And the reason we can do this is because our use of so-called modal basis functions. As in these cases, each basis functions is independent to each other, so therefore we can safely remove any of them without affecting the rest basis functions. So such refinement can be regarded as an alternative to the spatial refinement, except that now our adaptation is being made at the polynomial space, and therefore it maintains a very smooth spatial transition between the low-order approximation area and the high-order approximation area. And on the other hand, this sort of high-order refinement is numerically more efficient than the spatial refinement. And here is the result that we make in two-dimensional cases. In this case, we make a refinement up to the third order, and as can be seen, such refinement very effectively improves the singular value spectrums of the transform matrix. And this improvement then leads to a better inverse solutions. So here we show the relative error, RE, and correlation coefficient of our computed hard boundary potentials with the ground truth value. As it can be seen here, at each input noise levels, such P refinement actually reduces the error and increases the correlation coefficient of our solution. So therefore verifies the efficacy of our refinement scheme. So now I mostly end my first goal, and we now start looking at our second goal, which is to use PD-constrained optimization to solve our inverse problem. So what is PD-constrained optimization? The basic idea is, suppose we have a domain omega, and we have some physical quantities, ux and vx, defined over this domain. The u and v can be potential field or temperature field or some other physical variables. And suppose in this case, the vx is the control variable, and the ux is the state variable that depends on v. And their relationship is described by a partial differential equation system denoted as E here. And now the problem we're facing is we can measure the data of u at the boundary of the domain. And our inverse problem is to find the control variable v that yields our observed data. And the method we use is we minimize a certain functionals, j, of uv, and subject to the entire PD system, which comes in explicitly as a constraint. And this approach is in contrast with another approach that is more traditionally being used by the engineering people, That is, starting from the partial differential equations, we somehow explicitly derive a transfer operator K that direct maps your control variable V to your observed data, and then you somehow invert this process. So comparing these two approaches, you can see that the Ph.D. constraint optimization offers more flexibility for adding constraints, because now it exposes the whole underlying Ph.D. model for your manipulation, whereas in this case, most of the physical information is being hidden by this under this operator. And for our problem, the Vx becomes the transmembrane potential distributions within the heart volume, and the Ux becomes the extracellular potentials defined over in both the torso and in the heart. And our problem becomes from the body surface of U and try to get the distribution of V within the heart and use that information to try to localize a disease called myocardial ischemia. So now I explain this heart model that we used a little bit. We are using a static bidomain heart model, and the basic notion of bidomain is based on the knowledge of the cell tissues of the cell structures of heart tissues, which can be regarded as one intracellular space and one extracellular space. And the basic notion of bidomain is to homogenize these cellular structures by assuming that at each point of the heart volume, it is being simultaneously occupied by an intracellular space and an extracellular space. And both spaces are separated by a membrane. And there's a potential field associated with each space. So there's an extracellular potentials and intracellular potentials. And there's membrane potentials in between as well. Mathematically, it has been described as elliptic equations here. And the transmembrane potential distributions, V, in this case, forms the source term in this model. And this diagram shows a typical waveform of the transmembrane potentials at one point during one cardiac cycle. And the bidomain model can well represent the myocardial ischemia, which is a disease of heart tissue damage due to the insufficient blood supplies. Now, the myocardial ischemia is being characterized by the reduced amplitude in the action in the transmembrane potentials, as shown by this diagram. And in this study, we focused on the so-called plateau phase of the transmembrane potentials. So during this plateau phase, the heart potentials are rather stable. And in the healthy heart, the transmembrane potential distributions are also very homogeneous, almost constant. And if there's an ischemic region, then the transmembrane potentials in the ischemic region will have different levels of transmembrane potentials as compared with the healthy one. So that means in the presence of ischemia, usually we are expecting a piecewise constant feature of the transmembrane potentials. So if we can somehow reconstruct this feature, then we can get a good estimation of ischemic regions. This is the basic rationale of our inverse calculation. So now I review some of the related works in this area. The summary is that so far, very limited progress has been made on reconstructing the myocardial transmembrane source. In the first 4 studies here, the heart source model being used more or less restricts the behavior of transmembrane potentials so that the inverse problem can become less ill-posed. In the first study, the Bing-Heath group, they use a cellular automata to predetermine the behavior of transmembrane potentials. But this is a very oversimplification of the heart source, and is not very rigorously physically justified. And in their second approach, the Bing-Heath group, they try to pursue the so-called current density field, which is the gradient of the transmembrane potentials. But they obtained very poor and inaccurate results. For the Dussac group, they look at the time integral of the transmembrane potentials, rather than the potentials at one time instant. And in that way, they make the inverse problem more robust. And again, for the similar group, they used a level set method to characterize the ischemic regions. And that is also a simplified source model. And on the for the inverse calculation methodologies, most of these studies adopted the transform matrix approach for their inverse calculations, except for the last study, where those people did a pioneering job of introducing this PDE constraint optimization into the ECG field. And they apply this technique to directly pursue the transmembrane potentials at one time instant. But their pioneering work was limited in several senses. So they only did the simulations in two-dimensional models, and their optimization only allows quadratic objectives and equality forms. And in our work, we basically extended their pioneering work, and by generalizing their optimization frameworks and apply this technique to solve the inverse transmembrane potential problems in three-dimensional, more realistic situations. So here's a very a brief review of the results that we that obtained from the previous works. For the dual-cells group, they recover the time integral of transmembrane potentials. The left column are the ground truth, and the right two columns are the results they get. So it's not that close. And this is the pioneering work of using PDE constraint optimization. So even though they were using two-dimensional simulations, again, you can see their reconstructed data are very smoothed out as compared to their ground truth. So these results are not very satisfactory. And these are the current status quo on this pursuit for the transmembrane potentials. And we developed a general PDE optimization framework for our inverse calculation. And in our objective functionals, the first term is the misfit between our predicted data and measured data on the total surface. And any additional terms can be added here for regularization effects. And this framework has several features that are worth mentioning. The first thing is it is very flexible for adding constraints. This framework is essentially a convex optimization, so the only requirement for the constraints and for the objective functional is the convexity. But other than that, we allow constraints to be made on both the state variable u and the control variable v. And we allow both equality forms and inequality forms of constraint. So therefore, the users can easily incorporate their prior knowledge, say, of a potential field at a specific local region where they may have measurements or data, or they may add knowledge on a local place where they know the electrical currents. So we believe the flexibility for adding constraints may increase our chance to get a good inverse solution. And the second practice that we make is we separate the optimization and the discretization. And the reason for that is that we can ensure that our results are largely consistent when we did inverse calculations on the multiple resolutions and different discretization scales. And so we did optimization in the continuous space, and then we realized them by finding the element formulations. And we did this practice for two types of functionals. One is the quadratic Tikhonov functional, which is rather straightforward. And the second one is the total variation, which is not that straightforward. And actually, that is one of the contributions that we make. And I will talk this part later. And the third feature is we fulfilled the resulting numerical computation by a primordial method, that we developed all the block matrix structures for this method so as to exploit their numerical structures and improve the efficiency of computation. I will also talk this aspect later. And now I talk three aspects, technical aspects of PDE constraint optimization. The first thing is to combine optimization and finite element formulation. The basic notion here is we form the Lagrange functionals, and then we compute its derivatives and set its derivative to 0 and somehow solve the resulting equations. This is the basic pipeline of solving a constraint optimization problem. And the special thing here is the Lagrangian is a functional, and all its members, u, v, and p, are continuous functions. So the key notion of combining optimization and finite element formulation is that you do the finite element expansions for each of your member functions, u, v, and p, and you take Frechet derivatives of your Lagrangian functional in the direction of each of these basis functions. So such practice will result in a numerical systems like this. You don't need to go into the details of this math, and basically it says most of its member block matrices are defined in a finite element manner, and there are several very mature numerical solvers to solve this kind of problem. And in our case, we use a software package called SDPT3 for this kind of numerical optimization job. And the second aspect is how we handle total variation. The minimization of total variation involves the calculation of its Frechet derivatives. And because this derivative is highly nonlinear with respect to v, the total variation is by nature not well fit for finite element methods. And the way to handle this is to take an iterative approach where we linearized these derivative terms so that we can form our finite element formulations as we did before for quadratic objectives. And we repeatedly update this derivative term and solve the equation until some stopping criteria are met. So the key step here is how shall we linearize this term and update this term. And for this purpose, we developed two methods. One is the fixed point method, and the other one is the Newton method. For the fixed point method, we just fix the terms in the denominator by using the value of v in our last iteration, so that in this case, the only unknown terms is in the numerator, and which gives rise to a stiffness matrix with respect to the v. And essentially, the fixed point iteration is a quasi-Newton scheme in numerical optimization. So its convergence is guaranteed, and its convergence rate is superlinear. And for the second method, we use the Newtons, which computes the Hessian of the total variation terms. So the Hessian term is defined with respect to two perturbation functions, h1 and h2. And our computation mostly involves computing the terms in the bracket, which is defined as a 3×3 matrix at each point within the element. So I want to emphasize here, actually, that the Newton method is not a preferred way to directly solve the total variation, because its convergence domain is very small, so that you should wait a long time before you get convergence. And I do notice that there are several more advanced and better ways to solve total variations in the primal dual form or in the dual space, as proposed by, say, Tony Chan's group. But the value of our work here is such formulation of the Hessian term for the total variation with the finite element formulations. Such formulation can be easily adopted into those more advanced solvers for total variations. And that is, I think, the value of this work. And another important concern in this case is the computation cost. So in general, for both methods, they are too expensive to be practical. To see this, we realize that in each iteration in this iterative scheme, we need to recalculate the stiffness matrix of V, which is defined over the Hart volume. And Hart volume can easily reach millions or tens of millions elements. And what is even worse is that the gradient of V in general is not constant in each element. which means we need to use quadratures to evaluate the differentiation and then integration at each point. So that can be extremely computationally intensive. But the good news is that we find there's a special case that the computation becomes feasible. And that is the case for the linear, when the linear and tetrahedral elements are being used. We can see that in this case, the gradient V becomes a constant in each element, so that in the fixed point iteration, the denominator term becomes a constant in each element. And we can pre-compute our stiffness matrix and then quickly update this matrix in each iteration. And the same thing applies to the Newton's method, where the term in the bracket becomes a constant matrix in each element. So that again, we can very quickly update our stiffness matrix calculations. But we find that that's the only exception when even if we either we use high order element basis or use other shapes of elements, then your basis functions are no longer linear, and you have to use quadratures of all these calculations. So everything all of a sudden becomes extremely computationally expensive. And the third aspect is the primordial method for the numerical optimization. So don't worry about the math here. The basic message is we derive the block matrix structures in our formulation for the, so in our formulation for the optimality conditions and for building up this Newton system for calculating Newton step. So most of these block matrices are sparse matrices. So by deriving their structures, we try to exploit their sparsity structure and maximize our numerical efficiency for computation. So now I present some of the simulation results. So these simulations are closely coupled with experiments. In the experiment, we have a live dog heart, and we manually introduced ischemia into this heart by controlling the blood flows that feed in the heart. And at the same time, we measure the potentials both on the heart surface and within the myocardium volume. And the data, one of the data sets that we collected in the myocardium is shown here. And from the heart, we constructed geometries, and we also constructed an anisotropic conductivities based on the fiber structures of the same heart, which were derived from MRI scans. And for our simulation, we use a high-resolution model that ranges between 3,000 to 18,000 nodes. And that resolution is 10 times than the heart models that we have previously seen for this kind of inverse calculation. And this is one of the results we get with the synthetic data. So in the synthetic simulation, we just predetermine a region, assume that is ischemia. And we set up the transmembrane potentials in two levels. One is minus 30 millivolts for the ischemic region and 0 millivolts for the healthy region. So with this characterization of the heart potentials, we run our forward calculation to get the body surface potentials, and then we solve the inverse problem to recover the transmembrane potentials again. And from our recovered potentials, we identify the ischemic regions by a very simple thresholding. We just simply say at any point where the potentials is significantly below threshold, we regard them as ischemic regions. And so here we show the results we get for both the potentials and ischemic region estimation for two methods. The left one is the Tikhonov method, so it is more smoothed. And the right side is the total variation, which did a better job in recovering these sharp transitions between the healthy and ischemic area. And we also find the reconstructions are quite robust with respect to different input noise levels. So here, each row corresponds to the results that get at one input noise level. And here are the results we get for the real ischemia data. And the top row shows our ground truth of this is the extracellular potential, and these are the transmembrane potentials. So the extracellular potentials are what we actually measured, and the transmembrane potentials were calculated directly from the extracellular potentials. And this step is a well-posed problem. So we believe these are the ground truth of our transmembrane potentials. And the region of interest are at the bottom of these parts, where where the ischemia is located. And again, we get very promising reconstructed results for both the Tikhonov method and total variation method. So we largely captures this abnormal features at the bottom of the heart. And again, the solutions we get are very robust to the input noise. And this is another multi-scale test that we did. So previously, we did this 3,000 node heart. And in this case, we look at 2 finer heart models. And we can see that we obtained a very consistent reconstructions between these different models. And this largely thanks to our practice of separate optimization and discretization, so that the results are very consistent. And this is the multi-scale test for Tikhonov regularization. And this is the multi-scale test we did for our total variation formulation. So again, we obtained very consistent results. So in summary, in my thesis, we pursued 2 goals. The first goal is the finite element formulations for the inverse problem, and for which we developed a set of guidelines for carrying out the refinement. And we developed 2 techniques to realize those refinements. One is the use of hybrid-shaped elements, and the other one is to use the adapted high-order finite elements. And in our second goal, we build a general Ph.D. constraint optimization framework, and we apply that. We make the formulations and finite element solutions for that framework, and apply that technique into the case of localizing myocardial ischemia. And for future work, I think there are 3 aspects that are worth mentioning. The first thing is the Ph.D. constraint optimization. We find is very powerful, but it has not yet made its way into the bioelectric simulations community. And we can definitely think there are a lot of interesting problems that we can apply this technique to improve any reconstructions problems or inverse problems. And in our case, we consider the myocardial ischemia, which electrophysiologically is perhaps one of the simplest scenarios for bioelectric problems. And the more ambitious goal would be to try to reconstruct the action potentials during the whole cardiac cycle, and from which we can definitely use the results to look at more complicated heart diseases, such as arrhythmia or fibrillation. And the second part is more on the computation side. The Ph.D. constraint optimization involves repeatedly solving your PDEs, which is very time-consuming. And one area that is now under very active research is to combine adaptive PDE solvers with your optimization. That would usually means to change your meshes during each iteration of the optimization. And but what are the right criteria for adaptation? That still remains an open problem, and it's being under very active research now. And also, it is worth to couple the parallel computing and use GPUs to accelerate this whole computation process. And the third direction is to consider the statistical inverse problem for uncertainty quantification. And in our problem, we took a deterministic approach, whereas I think a statistical approach is a more broad modeling of the problem and better account for the uncertainties which are ubiquitous among the biological applications. And a particularly appealing prospect for this statistical formulation is perhaps our inverse problem can become much better posed Because in that case, we are looking at the possible distribution of all your possible solutions rather than a single instance of the solution. So therefore, I think perhaps it will become numerically easier to solve. But of course, that involves more an endeavor in the mathematical modeling side. So during all these years, I have a lot of people to thank. The first, of course, is two of my mentors who introduced me into this biomedical computing field. When I came to Utah, I have totally no idea what I'm going to do here. And also special thanks for Rob and Dana, who adopted me into their group, so that we sometimes meet even more frequently with my own advisors. And I'd like to thank Ross and Sarang for their inspirational discussions, particularly regarding the Ph.D. optimization part. And of course, my work would not become possible without the dirty job done by the Darryl and Kedar on doing those animal experiments and collecting data. And finally, I would like to thank my lab mates and all the ski people that gave me great assistance during all my studies these years. And thank you very much for your listening.
All right, we'll now take questions from the audience. So the floor is open for questions for Dafang. Questions? Rob, maybe.
One of them, first of all, it's fantastic work. I mean, you've done a really amazing job. You've acquired a very broad base of knowledge, and managed to cross this chasm between the computer science and the bioelectric bioengineering approaches, and it's it's really credit to your energy and your intelligence and your perseverance that you managed to do that. And I think this is work not only that builds on things that already existed, but that has a bright new future and a way to go forward. One of the questions I had was regarding the discretization approach you used, and you mentioned that, for example, there was 3 rules of discretization, and one of them was that you wanted to keep the resolution on the heart surface constant, even as you refined other regions of the
Yes.
torso.
Mm-hmm.
What's the basis for that? Did you play with that assumption? And
Yes, we place that, and there's a theoretical investigation as well. Let me just go back. Oops. Side is this. Yes. So we did. There's also a theoretical side of this research, but I did not elaborate on it. Is we did a Fourier analysis of these PDE systems, and the notion here is we find that the variable m are the spatial frequencies of the hard surface potentials that we want to pursue, and we find that the attenuation rate from heart to the body surface, which means it's the numerical conditioning of the problem, right, with the inverse. That's an exponential function with respect to the spatial frequencies. And meanwhile, the spatial frequency is dictated by the resolutions you take on the hard surface. Mm-hmm. So you can think of if each neighboring node on the hard surface is 1 minus and 1 positive, mm-hmm. you can get a very high oscillation mm-hmm. potential field. That's the worst case.
Right.
And but when you formulate your transform matrix, that your conditioning just reflects your worst case scenarios.
So do you end up with like a nice Nyquist type criteria?
Yeah, something very similar to Nyquist criteria.
Right.
Yeah.
So can you follow up on that and say what the optimal discretization is on the heart for an inverse problem?
Well, I would say that it only depends on your clinical needs, and my advice is that to carefully determine the resolutions you want to pursue based on your clinical needs, but be careful, do not to pursue too many fidelities, and don't be too ambitious.
Can you theoretically determine that? Mathematically, can you determine the optimal discretization from an information theoretic point of view or a Fourier analysis point of view?
I would not say that's optimal, but I would only say that follows some of the rules that we discovered. We can't beat the rules, of course.
More questions? Yes, Guido.
Mm-hmm.
Okay, I take this one. And then you have the real examples. Oh, yeah, we still have to adjust to this. Okay, the real examples where you showed the experiments, also with 3 different noise levels.
Yes.
That's just one, or how?
You mean in this case? For example, in this case?
Okay, yeah. So you say input noise level.
Yes.
So I somehow missed it, because if you have a real scenario, how do you choose the input noise level? Is it an estimate that you put into your scheme, or can you estimate
for the real
the noise
scenario, we just pick these hard potentials. So these are the real data that we collected from experiments.
Yep.
But for our simulation, the thing is, I can show you the simulation pipeline we did.
So probably that's the point that I missed. Yeah.
Yes. So this is a more this simulation is more on the phantom side. Okay. Yeah. So this is the basic simulation pipeline we take. So in this case, we use a real hard data, and you can plug into your simulation to get body surface potentials.
Yep.
And what I mean, input noise is I add noise to the body surface potentials we get. So we add those different levels of input noise here on the body surface, because that serves the input for our inverse calculations.
Okay, so that allows you to somehow determine the breakdown point, or
Oh yes.
But would you have an estimate? What is the noise in a real data set? If I would be a patient and you do the modeling, do we know the noise level in a real human experiment?
So I determine the noise level mostly from the literature. And from the literature, most people take 1% to 3%, 1% to 3% input noises. And but if you're only judging from your body surface electrodes, and from some of the manufacturers that I asked, they claim their measurement noise is like is well below 0.1%.
Okay.
But I have a little bit of suspicion on that, but I cannot verify that.
Okay.
So we somehow use a little bit higher noise level than those claimed by the vendors.
So how do you actually set that? I was curious about that too. So you take QRS as the 100% and then take an RMS white noise level at 3%, or how do you?
We just take white noise depends on our body surface potentials.
Right.
So it's when I say 1%, it strictly means the energy of the noise is 1% of the energy of the body surface potentials. But the noise at each nodes here are independent to each other.
Okay, thank you.
Oh, one more question, Chris. Yes, please.
Yes.
Sorry, can you speak louder?
Thank you.
Very last. Okay. Yeah.
Hey, Dana, we're going to the last 5 slides is the question. Wait 1 minute.
Is this one or like this one? Is this one? You mean? What do you mean? So which column are you referring to? Okay.
You'll need to repeat the question because we're not hearing anything.
So Dana, so we are now at the page 49, the multi-scale test with the real data. So your question is, why am I results not very closely matches the positions of yes, because these are two different methods. Hold on.
No, I think he's looking at, if you look at the real solution at the top, and if you look at the apex of the heart, that in your simulations, it looks like the left side is better. You resolve the solution better on at the bottom left of the apex of the heart.
Oh yeah, yes.
Than you do on the right side. And why is it that way?
And I think that is largely due to the different resolutions you take, because then, I mean your numerical problems have very different sizes. So I would attribute such variance to the numerical properties of those different systems. But in the past, when you take a very high resolution model, what you usually get is you only get some meaningful results only on the surface. You mostly lost most of the information in the volume. Whereas in this case, we largely preserve this volume information. Of course, that is not perfect. And yeah, I think that's my answer.
So can you say something about when we were talking about the errors that Guido said about 0.1 and 1% and 3% that you added? Where do you think the biggest errors are in your model?
The biggest errors are in my model? Well, there are several aspects. One is, of course, the data we collected. They already contain noise, and the data I obtained from those experiment people, they already have done some pre-processings to remove some noise and to register data into, and also we have to do some sort of interpolations to fill the data all over the heart, and that involves some uncertainties. And that's on the data source level, and on the simulation level, then I would argue that the geometries, particularly for the torsal geometries, I think there are an error. These are the sources of errors.
Dana, are there any questions from your general audience there at Northeastern?
Lots of shaking of heads. We can't hear you.
We can't hear you, Dana.
Questions? Yeah.
Hi, Dafang. It's Brock.
Hello, Brock.
Can't hear you. Can't hear you, Dana. Hi, Dafang. It's Brock.
I can hear you, but I can't see you. But that's fine.
So on slide 38, So on slide 38,
yes.
Sorry, there's a lot of delay. You listed a number of constraints, and you said that in particular you needed to have convex constraints and convex, cost functions. It looks like one of your flexible constraints, the third one in particular, has a norm constraint that's greater than some threshold. I don't think that's actually convex, is it?
I think it is convex because the norm, all the LP norms are convex functions, right?
It's, well, greater than, well, I mean, if G1 is greater than 0, I don't believe that's a convex function. Or sorry, a convex constraint.
That's to agree strictly. That is not convex. But in your numerical treatment, you can, if you can put your gradient operator into a linear algebra structure, then somehow you can represent your gradient v in a vector form. And in that case, you can safely put a discrete norms on it, and therefore that becomes a convex in the numerical sense. But I agree with you. If you look at it very strictly on the pure mathematical level, and that is not convex. But that's the way that I did for putting a local constraint on the gradient of a field, and tried that, and it worked well actually. So it's there are some of the numerical tricks that we did here.
Okay, are there any other questions from the general audience before we excuse people and just have the committee?
Look him up. Just tell me about it.
I mean, okay, it may be, I mean, it may be locally convex, but yeah, I don't know. I don't know. I don't know if you can see in the video, but someone at the end of the table disagrees more than I do. But, anyways, I guess we can have an offline discussion about that one.
Yeah, I'll just add. So there's definitely some question about that contention in this room, but we can talk about it offline if you want.
Okay, sure.
Okay, well, let's thank Dafang again, and we'll excuse the general audience. So,
Well, excuse the